For this presentation, we have Kyla Edison. She's a Geology and Material Science Technician at Pacific International Space Center for Exploration Systems. And she is going to tell us about validating the sinterability of lunar Martian regolith for ISRU by characterizing Hawaiian basalts. Take it away, Kyla.
Okay. So hi, everyone. My name is Kyla Edison. I am the Geology and Material Science Technician for the Pacific International Space Center for Exploration Systems, also known as PISCES. We're a state-funded aerospace agency located in Hilo, Hawaii, so aloha from Hawaii. Today, I'm going to talk to you about validating the sinterability of lunar Martian regolith for ISRU by characterizing Hawaiian basalts. So basically, the whole idea behind this research is can we make a durable construction material from basically any basalt that is lying around? And is that, is it dependent on chemical composition or not? So to do this, we're using the Island of Hawai'i, or the Big Island, as kind of like a analog site. I have gone around the island and sampled from 4 quarry sites already. They're commercial quarries already disturbed. They're located in various areas of the island, as well as 3 analog sites. They're lunar Martian analog sites, usually pretty chemically similar to what you find on the Moon and Mars. And these analog sites are used for various things like field test operations. One of them is used for the isolation missions at high seas, that kind of stuff. So if you look chemically, the Hawaiian samples compared to the Moon and Mars are pretty similar. There are some obvious variations in chemical composition, but for the most part, they are pretty similar. So that's why we've decided to use our basalts here for this project. If you plot these rocks from Mars, Moon, and Hawaii on a TAS diagram, you can see where they fall, and you can see what types of basalts or basalt categories they're falling in. And so using this idea, I just kind of go center, figure out the chemical composition, and then just based on that, what materials are coming out the best, and then can we find that on the Moon and Mars? So if we start with the quarries, these are going to be your typical basalts. So these are just typical basalts. Your analog sites are a little bit different, and I'll get to that here in a little bit. But basically what you do, I sampled these and then just went straight to sintering. When this project was first started, we used material from Quarry 1 here, this small sample here. It was used in collaboration with SwampWorks as a static launch pad test. It was the only basalt that was used at the time. Funnily enough, it was also kind of the best. They hadn't tested anything else, so it's kind of funny that it is actually our best material. It sinters really well. When they did the test, the launch pad itself, the design of the tiles flew all over the place, but the tiles themselves weren't damaged or weren't heavily damaged, and they kind of came away unscathed. After that test, we decided to go around and actually do the sampling around the island to see if we could get the same kind of material. And as you can see in these photos, there is quite a difference between all of the quarries that I sampled. Some of them are, I mean, clearly better than others. Quarry 2B, you can see like it looks like if you were to touch it, it would fall apart. Same with Quarry 4, whereas Quarry 3 looks a little bit better. But Quarry 1 still definitely, in my opinion, looks the best. So when we put these things to the test, we did a compressional and flexural strength testing on these things, and you can see just from the data that Quarry 1 compressionally was comparable or did a little bit better than your commercial concretes, whereas the Quarry 4 material did really, really poorly. And so we needed to kind of figure out why that was, because the processes to sinter all of these things were the same. Grain size was about the same, temperature was about the same, all of that was about the same, but we were getting different results for all of this stuff. And I'll kind of continue with that in just a second. After that test was done, we had decided maybe if we bring the temperature up a little bit more, maybe that'll change the material, or maybe it'll make it stronger. So they started again with just Quarry 1 material. At the time when they did this, that was the only material that they had at the time. So we sintered at only 30 degrees C more and came out with basically a different material, different in color, different in strength, and also different in the fact that every time that we would sinter, this material would crack. And so we had this really strong material compressionally that did, you know, that just blew special concrete out of the water, but it just kept cracking. And so we needed to figure out why and how to stop that, and if it was possible to stop it. And so again, using different materials from different quarries and changing the sintering process a little bit, we figured out how to kind of come out with this material that wasn't cracking. And so you can see Quarry 1 and Quarry 3, they're very similar looking. And Quarry 4 is very cracked and still isn't doing very well with sintering. Basically what we ended up doing is with the lower temperature material, we were sintering, bringing that stuff up to temperature, kind of letting it hold for a certain amount of time, and then just kind of letting it cool naturally. That works at lower temperatures, but even just adding the 30 degrees, you're raising the temperature such that it's becoming hot enough that when it cools, if you let it cool naturally, you're basically subjecting it through thermal shock. And so in the oven itself, it just completely shatters. So my idea to kind of mitigate that was thinking about what makes a really strong stone, just like in nature. And the example that I always come back to are granite countertops. We have granite countertops because they're very durable, they're very, very strong. And the reason that is because you have these interlocking crystals. They're very big, they interlock, and it makes it very, very durable. The only way that you're going to be able to get that kind of stone is if you allow it to cool at a very, very slow rate. So obviously granite has like thousands to millions of years to cool, where you don't have that kind of time in the kiln. So all that I did was just bring that cooling temperature down as much as I possibly could, and for the shortest amount of time. And so that seemed to help, and we were able to make this really nice cohesive material. And applying that that technique to the other quarry materials, you don't get the same result. So you're starting to see a pattern of, for some reason, Quarry 1 and Quarry 3 are creating this really nice material, whereas quarry 4 is not. It just doesn't sinter very well. So I go back and I look at the chemistry of these basalts, and you can see very clearly the magnesium oxide for two of our basalts are very, very high, and those end up being quarry 4 and quarry 2. I'm going to not talk about quarry 2 as much, just because we don't have that material available to us anymore, so I haven't been able to do any more analysis on it. So we'll just focus on quarry 4. And so looking at that magnesium oxide spike, kind of thought about why that could be, like what's in basalt that would cause such a spike. And the only thing that I could keep coming back to was olivine content. And so my focus then became, how does an abundance of olivine affect sinterability? And so in this photo that you see is a thin section of quarry 4. And you can see all the colorful, really nice crystals there. Those are all olivine. And so basically what we did was we subjected all of our materials to X-ray diffraction to get a better idea of exactly what the crystallography of this stuff was, the mineralogy of this stuff was. And if we look at olivine, specifically forsterite, which is the magnesium end member of the olivine, it's the most common type of olivine you're going to find in these Hawaiian basalts. The melting point for that is 1890 C. That's a really, really high melting point, especially when considering that the highest temperature I'm sintering at is only 1177 C. And so looking at the XRD analysis, you'll see that quarry 1 and quarry 3 have 0% olivine, where that's not necessarily true. There is olivine in these samples. The amount of olivine that's in it is just about negligible. We're not finding olivine within the matrix of this stuff. We're just finding little pieces of olivine here and there. So basically the olivine content in these two materials are extremely low. They have very high plagioclase and you know, a fair amount of pyroxene and a fair amount of glass. But if you look at quarry 4, it has 33.6% olivine, which is really high comparative to quarry 1 and quarry 3. And so it started to kind of make sense that, yeah, maybe olivine is the true culprit for a very bad material. And so the idea was that you have in a sample that's rich in olivine, when you sinter, the basalt grains during the sintering process begin to fuse. And they kind of start to mesh together. Whereas if you have a large percent of olivine, that olivine isn't necessarily sintering or melting, it's just kind of sitting there and warming up. And when it's not sintering, you're creating these huge gaps, which is probably causing the poor structure of the material. So I wanted to test this idea, and I wanted to do like the most extreme case that I could. So I went to the southern point of the island where there was a pickrite flow. A pickrite is basically just a basalt that is enriched with olivine. You can see in the photo, you have your typical basalt, but there is an abundance of olivine. So I collected these samples, I ground them down, and I put them into my kiln, and just to see what would happen. I did it at the lowest temperature possible, just to kind of see what would happen. It's the easiest thermal profile to work with. And you can see that the brick that came out, it's sintered, I guess, in a way. But you can see, like, I can touch it and grains will fall off readily. it's very brittle to touch. It falls apart. It just doesn't look as nice as the other tiles that I have. And when you look at it up close, you can kind of see the grains are just kind of connected. They're not really melted within each other. They're just kind of sitting on top of each other. And I believe that is due definitely to the olivine. So this was something that is very important. So if we have a basalt that is abundant in olivine, that might not be the best basalt to sinter with. And so then moving on to the analog sites, where the quarry material was your true basalts, the analog sites are more of a basalt scoria. Basalt scoria is a little bit different. Scoria is formed at vent eruptions. So it's the stuff that is being blasted out of a vent. As soon as it hits the air, it vitrifies. So it's basically made up of broken up crystals and a lot of volcanic glass. And so I wanted to see if that would have any impact on the tiles that I was making. And so just starting off with my lowest temperature, we subjected these to sintering again. Same process, just 1149, hold it for a certain amount of time and then let it cool naturally. And you can see that it comes out completely vitrified. It's just like these big blocks of glass. And so they didn't come out very well. They're very hard, but they are very sharp. They're very glassy. And so if we look at the XRD for that stuff, you can see again, there's like no olivine in this stuff. There's lots of plage and there's a lot of glass. And so I was thinking that maybe the glass is the reason for this very melted, very obviously glassy material. So to kind of play around with this, I dropped the temperature. So I went with the lowest I could at 1066, and you can see that nothing really happened. It's literally like dirt. It didn't sinter at all. You can seriously just break that and it crumbles completely. So then I just raised the temperature up to 1121 and then again at 1135. And these two materials are more reminiscent of my, my 1149 and 1177 material, except that they're made with basalt scoria. Again, these aren't maybe as nice as the Quarry 1 and Quarry 3 materials, but they did sinter, and I think they sintered well. They still need to go through structural testing to actually see just how durable they are, or if they're durable at all. But these are really hard materials just to the touch. You know, if you drop them, they don't necessarily break on impact. And they both, basically what this is teaching me is that you can take a basalt of basically any composition and it will technically sinter. It's to what grade of sintering that you're going to get. So if we were to go to Mars or the moon and we were to find, you know, a composition of basalt that was high in olivine, we could basically say like, okay, we might not want to sinter this basalt. But if we found one that was high in glass and, you know, that's all that we had, maybe we could use that as maybe a temporary material or a material to use for something that doesn't need something so durable. But clearly the high plagioclase, low olivine, and moderate glass content basalt is what's looking like the most ideal for you know, maybe a launch pad or foundation work or some kind of durable infrastructure that we would need on the moon and Mars. And so the next step from after sintering for all of this was to take those results, go back to the task diagram, and see where all of this fit in. So in the basaltic andesite category is where our quarry 1 and quarry 3 material fall, as well as our analog 1 and analog 2 material. That's also where the Mars Pathfinder data falls as well. So it looks like these types of basalts are the types of basalts that are going to give us the best building materials, or at least the materials that are going to sinter the best. The other stuff like quarry 4, like I said, if it has a high olivine content, it's just not going to be a good material to work with. So next kind of steps are to get better data sets for the Moon and Mars and do more comparisons from the Hawaiian basalts that I have and compare them to what is actually on the Moon and Mars, and can we find a quarry 1, quarry 3-esque material on these planets, and can we make the same level of tile as I do here in Hawaii on those other places. And so my conclusions to this, again, too much olivine in a sample does not sinter well. A low olivine and high glass content actually drives the sintering temperature down, which is also maybe beneficial. These high glassy materials, you know, I was able to drop the temperature down, which could possibly save on energy. But like I said before, the quarry 1 and quarry 3 materials are probably the best that I have, and they tend to be the most durable. But moving forward with that stuff, I want to perfect the sintering process for more consistent tiles that we can make at a volume quickly. I would like to continue to test the tiles capabilities. So we're looking at thermal shock, structural heat capacity, thermal conductivity, thermal expansion, and absorbency. And then also mixing basalt compositions. So like maybe we have a high olivine content basalt, you know, and that's maybe something, one of the only things we can get, but then we have also a high glassy basalt or basalt scoria. Can we mix the two to kind of create a different type of composition that'll still sinter well? Or do we have to find a mining site for these basalts? Like, will this one basalt only work, or can we mix them to make something that'll work okay for what we need? So for that, that's all I have for you today, and I'll take any questions.
A great presentation. Thanks, Kyla.
Thank you.
All right, looks like Calvin wrote, how do you imagine sintering will be done on the lunar or Martian surface? I'm guessing that focused solar energy is the most likely to be able to produce the temperatures required. Did you test sintering techniques in a vacuum and how they might perform different from pressures on Earth?
So right, one of the things that I do hope to do in the future is vacuum sintering. Although I also do realize that sintering may not be possible on the Moon or Mars. We're using sintering more as like a proof of concept. This is a good way for us to see the compositions of basalts and how they're going to behave under these temperatures and under these thermal profiles. So it actually might not be possible for us to sinter, but the important thing to understand is, does composition and mineralogy play a key role in the durability of a material?
Great.
Actually, if I can jump in for a second,
sure.
Ben, it's how to manage the sintering on the Moon or Mars. I mean, there's going to be different options for power availability on the Moon. Earlier talks have mentioned about the possibility of having nuclear small power plants on the Moon. That's one option. Definitely, solar concentrators can reach the temperatures required for sintering as well. And then there's also work that can be done using microwaves to achieve the sintering. So it's definitely not out of the question. I think the main purpose behind this study is that in the past, we've heard over and over again, sintering is a way to produce manufacturing materials or construction materials on the Moon or Mars. And people just seem to assume that wherever you land, you're going to be able to sinter the regolith. So the question that came up was, well, is all regolith created equal? And if there's any differences in the composition of the regolith, is that going to have an effect on the sinterability of it? So right now, like Kyla mentioned, we're in the proof of concept just to try to demonstrate or find out if indeed slight changes in composition of the basalt or the regolith will have a significant effect on the sintered material. And the answer is yes, it's quite significant. So I will disagree with Kyla on that. It may not be possible. I think it is very possible to achieve sintering on Moon or Mars. It is without a doubt an energy intensive process. That's no question about it. But yeah, we still need to test it on a vacuum environment to see what the effects are. And other work that we're currently involved with right now is trying to test a binder that we believe can be synthesized from in situ resources, and that could allow us to either lower the sintering temperature or eliminate it altogether.
Mm-hmm.
Great. Chris asks, have you considered using a process like a shake table or gravity separation to remove some of the olivine from quarry sample 4 to see if that improves cohesion?
So that's definitely something that I've actually talked to a lot of people about. I think the idea of electrolysis has come up quite a bit. That is something that I would be very interested in. It's just we don't really have the capabilities to do that right now. And so it's just been about trying to find basalts without the olivine. But yes, it has come up several times that maybe we can just, if we do land in an area, say with a high amount of olivine, can we get rid of it? And can that olivine be used for something else and not just wasted?
Great. And Bruce had a question. He asked, Mars dust is likely to be mixed planet-wide over billions of years, so it may be uniform. Do you know how well it will sinter?
No, no, I don't. So that's actually kind of where I'm at right now in looking at different data sets of Mars, trying to see what those compositions are, and then moving on to sintering simulants rather than just Hawaiian basalts to kind of see what, as close as possible to what Martian regolith would be like and how that might sinter.
And if I may add, to say that the Mars regolith is being mixed over billions of years and may be uniform, it only takes very slight variations in the mineralogy of the basalt to have significant effects. So we got to be careful and choose to assume that Mars is a single composition of regolith all throughout. We do have to find out, precise composition of different places in Mars, and then based on that, do a map that would allow us to determine which provide the most sinterable materials. Just to say that it's all mixed into a single recipe, I think it's not realistic.
Right, and just like Hawaii, Mars is basically the same type of volcanic activity. So you have areas where, say around Olympus Mons, for example, it's very comparable to our mountain here, Mauna Loa, where Mauna Loa, that gave me my quarry 1 and quarry 3 material, but it also gave me my pickrite material. So it just depends on behavior of the volcanic material, the volcano itself, and the material that it erupted. And, even though it's had a lot of time to mix and all of that, it's still very likely that you have different compositions. And I'm seeing that from the data sets that I have and putting them into those task diagrams.
Okay. Mark, you got your hand up. Do you want to unmute and ask your question?
Yes, well, thank you very much, Kyla. Nice to see you again. Thank you for
Oh,
the
hey.
presentation. I was wondering if you also looked at other high melting point minerals, such as spinel, which is also quite abundant, I guess, here in the mantle and also on the moon.
Yeah, so that is actually something that I am looking at, but for this presentation purpose, I just really wanted to get the information out about the olivine. But yes, I am looking at also pyroxenes, spinel, and the other constituents of basalts that are going into this. What I've noticed with Hawaiian basalts, though, the spinel content is very small, but there's still a lot of work to be done there with looking deeper into the mineralogy.
Great. Does anybody else have any more questions?
If I may, I actually have another question as well.
Go for it.
Did you also look at higher temperature melting points, like maybe up it to 1400, 1500 degrees Celsius? Or doesn't it work? Do you have pure glass then?
So do you mean like bringing the sintering temperature up?
Yeah.
So I have thought about that, but when we're thinking about the moon and Mars, right, we want to be as energy efficient as possible. So I felt as though if we were to bring the temperature up higher, which it's already very difficult to sinter at the 1177 temperature, it to me seems pointless to go any higher, just because of the fact that we're doing this for the moon and Mars, right? We want to be we don't want to use as much energy as possible. And so right now, that highest temperature seems to be, you know, as far as I want to go, especially because it is very hard to sinter at that temperature already. I still have a lot of issues with it, from sticking to molds to I still get cracking in the oven as well.
If I may add to that, the other thing is that sintering is a process by which you approach liquefaction of your grains. If you increase the temperature past the sintering point, you enter into the melting point or liquefaction of the material. That's a completely different process. Now, that does not mean that you cannot consider melting and casting as a different option for producing a material. But once you can't increase the sintering temperature, because the sintering point of a material is given by its physical chemical properties. If you pass the sintering point, you get into the melting point, and that's a completely different process.
All right, everyone. Well, if we don't have any more questions, we'll wrap this up. Thanks, Kyla. That was a great presentation.
Thank you.
Appreciate it. And thanks everyone for being here.